Howdy! This short little video is going to take you through how to work problem number 4 on homework number 2. If you remember, we talked about this very briefly in class and said that one of the assignments is to download a data file from the Canvas website and process it for several of these various items that are listed as A through I below problem number 4. Some of the items include things like pressure versus volume, the engine's compression ratio, net indicated mean effective pressure, gross indicated mean effective pressure, so on and so forth. So this video will take you through how you actually process that pressure data and calculate some of these parameters. So along with the homework being listed on Canvas, there's also a data file, and that data file is a .txt file, which you can import into any software that you like that can do calculations. You could import it into MATLAB if you wanted to, or you could code a Python script. I find it easiest to just do this in Excel, and so I've imported the file into Excel. And there's a few things that you can note in the file. The first line that you see here is just the name of the test that I was conducting. I took this data long time ago, almost 20 years ago, that was part of my PhD studies. And so this was just the name of the file, the condition that I was operating the engine at. And this, of course, was the date and the time that the data was taken. And this averaged number of cycles isn't so much important for this assignment. Just for your curiosity, what that means is the engine recorded 20 individual consecutive cycles, or the data acquisition system recorded 20 individual cycles, and then the post-processing software took those 20 individual cycles and averaged them, and then gave the output that you see below here, which I'll go over in just a moment. There's other items that are included in the Excel spreadsheet, such as the clearance volume of the cylinder, the bore, the stroke, the connecting rod length, the wrist pin offset, the speed, and the brake torque. And each of these that are listed in this spreadsheet will be used by you to do problem number 4 in homework number 2, okay? Now, one common question is, if you read the problem statement closely, you'll note that it says that the data was collected from a 1.7 liter four-cylinder diesel engine. And at some point, we have to calculate the displaced volume for a given cylinder. So very often what students will do is they'll just take this 1.7 and divide it by 4 and provide a per cylinder displaced volume. Well, that's sort of correct. It's only correct in an average way. This 1.7 liters, first, that's not the precise displacement of the engine. That's basically a close enough number of the displacement of the engine. Each individual cylinder can have its own individual displacement that when you add them all up comes close to 1.7, but doesn't come precisely to 1.7. And furthermore, not every cylinder has exactly the same displacement, right? There can be some differences among each cylinder, where some cylinders will have higher or lower displacements. And so this 1.7 liters that you see here, that's a rough estimate of the total displacement of the engine. And if you divide it by the number of cylinders, you're only getting an average displacement of the of each individual cylinder, not the actual displacement of each individual cylinder. But the data that's given to you here in the spreadsheet, that will allow you to calculate the displacement of the cylinder from which this data are taken. And so that clearance volume is the clearance volume of the cylinder. The bore and the stroke are nominally the same for each cylinder. The clearance volume is really where the displacement and the total, the volumes really get strongly impacted. Okay, and so you'll want to use these data here to calculate the various volume parameters for your calculations. Another question that often comes up is, you'll notice that the wrist pin offset is provided in the spreadsheet. A wrist pin offset is essentially a purposeful offset provided into the piston connecting rod connection to help balance the forces when the piston is under compression or expansion. Okay, so let me just very quickly draw that for you so that you have some sense as to what I mean by that. So, for example, if say this is our cylinder and this is our piston, we'll sort of just always assume that the connecting rod is connecting to the piston with the wrist pin right in the middle of the piston, okay? But that's actually not correct. Very often what is done is an offset is purposefully built in. And so if this is the center line of the piston, your wrist pin might actually be slightly offset. And this is a bit exaggerated because I wanted to be able to show you visually what that looks like. But this difference between the center line of the wrist pin and the center line of the piston is what we call the wrist pin offset. And it's provided to you only because it's a complete way of characterizing the volume calculation for the cylinder. In fact, you can basically see how small it is, right? It's less than a millimeter of an offset. So it's very, very tiny. But it's just enough to, as I mentioned, the reason why this is done is when you have forces applied onto the face of the piston, of course, the side force on the piston will have a tendency to push in this direction, right? But when the piston is going up, and the forces reverse, then it pushes the side forces to the other side of the piston. And so it helps to balance the forces that occur on the sidewall of the cylinders while the piston is reciprocating back and forth inside the cylinder, okay? But again, it's very, very small, and even though it's non-zero, the effect on the volume calculation is pretty tiny, right? And so you certainly could adjust your kinematic relations to account for that offset, that delta, if you wanted to, but what you would find is that it has a pretty small impact on the volume and ultimately the mean effective pressure calculations. If we were doing a more rigorous simulation of this engine, we would want to include that wrist pin offset, but for the purposes of this assignment, you can ignore that wrist pin offset. Okay, so if we now go to the various items that are being asked, of course, one of the items that we're being asked to provide is the pressure versus volume plot, okay? So if we look back in our data file, we have pressure as a function of crankshaft position, okay? So this is pressure versus CA, pressure versus crank angle, okay? Pressure is given in bar and the crankshaft position is given in degrees. And you'll notice that the crankshaft position is or I should say the pressure data are logged every quarter turn of the crankshaft, right? And so you can scroll through this whole set of data and it's going to go from minus 360 to positive 360 at the very bottom of the data file, okay? And it gives the pressure behavior along that whole crank angle sweep. So you can plot pressure versus crank angle, and in doing so, what you would get is basically a figure that looks something like the following. So this is crank angle in degrees, and this is pressure in, say, bar. I'm not going to put any values on it, but you can assume that this would be pressure in bar. And our data file starts at minus 360. Of course, we have 0 degrees here, and our data file ends at plus 360. And so if you were to plot that pressure versus crank angle, you would essentially find something that looks like this, okay? And you can go ahead and do that and take a look at it. But what's important is that the minus 360 is the start of the one cycle. And so the piston is at top dead center here, intake valve open. You have your intake stroke until about 180 degrees. Valve closes, you then have compression until you reach top dead center again at 0 degrees. You have combustion taking place, expansion, and then your exhaust valve opens somewhere around 540 degrees. Excuse me, not 540 degrees, plus 180 degrees. Sorry about that. This is 180 degrees. And then exhaust valve closes somewhere around 360 degrees. Intake valve for the next cycle opens, and then the cycle repeats itself, right? And so this is the data that's given to you. In the Excel spreadsheet, the data that's given to you is this pressure versus crank angle, okay? But if you look at the assignment, it's asking for pressure versus volume. So the first thing that you need to do is you need to take your crankshaft position along with the bore, the stroke, the conrod length, and the clearance volume, and you need to use the kinematic relations that are given to you in your Chapter 2 notes, which have been posted to Canvas, okay? So if you take a look on Canvas, you'll note that there is a slide that says crank slider relationships, and in the middle of that slide, there is this relationship that gives you volume with respect to clearance volume, VC stands for clearance volume, is equal to this big, long trigonometric relationship, okay? Now we'll go over this in class and talk about how this trig relationship is developed, but you can see that the various parameters that you see listed here, if you go back up a few more slides, you can see where these various terms are defined for you. So the little r is the compression ratio, L is the connecting rod length, A is the crank radius, okay? And so going back to our kinematic relationships, right, you can see that L is the connecting rod length, A is the crank radius, A appears as crank radius here as well. And then, of course, theta is the crankshaft position, right? So again, going back to that little diagram that we were just looking at, you can see that theta is defined here as the angle between the vertical line and the crankshaft position at any given moment in time, okay? And so that's theta. And so you can basically use theta from your Excel spreadsheet, right? So the theta that you have here, along with this relationship and the compression ratio, little r, and this big term, or this term, big R, which is just the connecting rod length L divided by the crank radius, okay? So you have everything, and of course clearance volume is given to you in the Excel spreadsheet. So you have everything that you need to use this trigonometric relationship to calculate volume as a function of crank angle, right? So first thing that you want to do is create a new column here, right, which is volume, if I could type, volume in cubic meters, right, and then use your crank angle along with this relationship and the clearance volume that's given to you to calculate your volume as a function of crank angle, okay? So then, of course, once you have pressure and volume, now you can complete part A, which is just the pressure versus volume plot. Part B is the engine's compression ratio, right? That's just the maximum volume divided by the minimum volume. And again, you're going to want to use the data that you calculate in the spreadsheet. And so you can just use the max-min function. If you're using Excel, for example, you can just find the maximum volume that's calculated in this column and then divided by the minimum volume that's also calculated in this column, which will be the same as the clearance volume. The clearance volume and the minimum volume are the same thing. Okay, now it gets particularly interesting when you're asked to calculate the net indicated mean effective pressure and the gross indicated mean effective pressure, two parameters which we'll call net IMEP and gross IMEP, and then the pumping mean effective pressure, or PMEP, okay, now this is a little bit more involved in terms of how we calculate it. And so what we start with, and again, I'll cover this somewhat briefly. I'll go over IMEP in large detail in class, but in terms of how you calculate it from this data set, this short little video is going to cover that in greater detail, okay? And so first of all, what we need to know is that mean effective pressure in general, okay? And there's lots of different ways that we are going to characterize mean effective pressure. And we'll talk about this in class, right? There's obviously indicated mean effective pressure. That's what we're working on right now. But there's also brake mean effective pressure and friction mean effective pressure and pumping mean effective pressure. So we'll define all of these in class, okay? But in general, there's this term called mean effective pressure. And what mean effective pressure, when we look at how it's calculated, it's simply the work of a cycle divided by the displaced volume of that cycle. Okay, and what this is based on, if you remember back in your first course in thermodynamics, right, you have a pressure versus volume diagram, and you might have a pressure versus volume diagram that looks like what it looks like in an engine, right? So that would be our compression stroke. This is combustion and expansion stroke. And then we have our exhaust stroke, and then we come back and have our intake stroke, right? So this is sort of what the pressure versus volume diagram will look like when you plot it in your Excel spreadsheet, okay? Now you'll also remember that work is the integral of pressure times change in volume, okay? And remember, when you took Calculus 152, that the integral is just the area under the curve that's being integrated, right? So our work is basically the area that's captured between these curves that are formed from compression and expansion, as well as the intake and exhaust stroke, which is pretty tiny down here at the bottom, okay? Okay, so what mean effective pressure is doing is it's taking this work term and it's dividing it by the displaced volume, right? So we can go ahead and draw our displaced volume. Here's the minimum volume, and here's the maximum volume. And so remember that displaced volume is just the maximum volume minus the minimum volume, okay? And so this difference here between maximum volume and min volume is just the displaced volume. So what the mean effective pressure is doing is it's basically identifying an average pressure where if that stroke was constant pressure, that constant pressure times the displaced volume would equal the work under the actual curve that is occurring, okay? So I know that was super confusing, okay? I'm sorry. Another way to say it is that there's an actual work relationship here, right? Which is the integral of PdV, okay? Well, that work, the integral of PdV, is equal to the mean effective pressure times the displaced volume, okay? So the area under this curve, the actual curve, okay, this curve here, you can't see my pen. So that, this part here, the area under that curve is equal to the area under this curve, okay? The area under the mean effective pressure curve. So the basic idea is that mean effective pressure is giving you some sense as to how much work the cycle is making, okay? The higher the mean effective pressure, the more work of the cycle, and vice versa, okay? Okay, so now we'll talk about the difference between brake mean effective pressure and indicated mean effective pressure. But for the purposes of the assignment that we're looking at right now, we're being asked to calculate the net indicated mean effective pressure, okay? So for the moment, ignore the net and the gross and the pumping and all that stuff, okay? Let's just focus on the indicated mean effective pressure, okay? So the indicated mean effective pressure is that mean effective pressure that's calculated from an indicator diagram, okay? So what's an indicator diagram? Well, not going through a whole history lesson here, but basically an indicator diagram was a means to scribe, literally pen out with an indicator pen on graph paper through a mechanical linkage into the cylinder contents, right? There was a mechanical diaphragm that would translate the pressure of the cylinder onto a pen that was literally scratching out or scribing out the pressure on graph paper as the engine was running, right? And so the engineer would be running the engine, and this indicator pen would be scribing out the pressure on graph paper, basically on a roll of graph paper, and it was called an indicator diagram because it was being indicated. The pressure of the cylinder was being indicated on this diagram, and then the engineer could go in and, using geometrical relationships and other means, calculate the area under the curve, and that would indicate the work, right? And then correspondingly calculate the mean effective pressure. Okay, well, fortunately, we've advanced since those days, and of course, now we have electronic pressure transducers and electronic data acquisition systems and outstanding software made by great companies like Microsoft to give us software like Excel, where we can now do all of this electronically and digitally, right? And so for the purposes of this assignment, when you see those words, the indicated mean effective pressure, right, whether it's net or gross, you're going to be calculating that mean effective pressure from this Excel data, okay, from the crankshaft, cylinder, volume, pressure volume data that's given to you or that you're calculating in your data sheet here, okay? All right, so now how do we actually calculate the mean effective pressure from these data, from particularly pressure volume data, okay? Well, let's remember how our mean effective pressure is defined, right? Mean effective pressure is defined as the work of the cycle divided by the displaced volume, okay? All right, well, I can get displaced volume. That's pretty easy. How do I get the work of the cycle, okay? Well, I turn to my one of my favorite thermodynamic relationships, which is that work is the integral of PdV, right? So, but okay, that makes sense. But now how do I apply this expression, particularly this integral sign, right? How do I apply this expression to calculate the work of the cycle, okay? Well, there's several ways to do that, and there's a best way to do it. One of the several ways that students try to do is they'll try to fit this curve that you see here in the pressure volume diagram. I'm trying to scribe over here. I'll do it with a different colored pen so that you can see it, right? They try to fit an equation like a spline, for example, to that expression, to this functional behavior, or they'll split it up, right? And they'll say, okay, well, this is an equation, and then this is an equation, and then this is an equation, and then integrate them with respect to volume, and then add it all together, and right? Okay, no, that's not the right way to do this, okay? The right way to do this is instead to do, more or less a Riemann sum, right? Or a numerical approximation to an integration, okay? So in other words, rather than write that the work is the integral of PdV, what we're going to do is we're going to say that the work is equal to the sum of the pressure times the change in volume, okay? So now all of a sudden we've taken, this infinitesimally small change in volume and we've made it a finite change in volume. And we've taken this infinite sum and we've made it a finite sum, okay? And so now what we do, right, is we say, okay, well, I need to have a pressure times change in volume, okay? And so I can go back to my Excel spreadsheet, and just like I had the volume relationship, I can create a little work column here, right? And I can say, okay, well, this is just going to be, say, for example, this pressure times the change in this volume relative to that volume, okay? So that would be called a left-hand sum. Or if you wanted to do a right-hand sum, you could take this pressure and multiply it by the same change in volume, this volume minus this volume, right? And that would be called a right-hand sum. Or you could, do the midpoint rule, right, where you take the average of these two pressures, for example, and then multiply that by your change in volume, okay? So, you could, there's different ways of increasing the accuracy of this numerical integration. You don't have to, and by the way, that last technique is called the midpoint rule. You don't have to do anything more extensive than the midpoint rule. But, you do need to basically create the work that's associated with that change in volume over that quarter change of the crankshaft position, right? And so you then basically use your little fill function, right, and fill all the way down. Be very careful at the very, very, very bottom of the spreadsheet, right, because you're going to be calculating the difference between, you might be calculating the difference between this cell and that cell. Well, this cell is empty, right? There's going to be no volume in this cell, so you need to make sure that you resolve that. It's a pretty indetectable error, but it would be an error nonetheless, right? And so you just fill this work column all the way down to the bottom of your spreadsheet, and then now you can do your summation, right? So again, let's go back to our calculation for work, right? And so we can then say that a certain amount of work is going to be the sum of that pressure times the change in volume, okay? And now this is where it becomes a difference of gross work versus net work, okay? So, and again, we'll define this in class, but gross work is only that work associated with compression and expansion, and so to calculate the gross work, it's going to be the sum from I equals negative 180 to positive 180. And the work at the pressure at that moment times the change in volume at that iteration, okay? Okay, so why did I say minus 180 and plus 180? Well, if you remember, if we go back up here to our pressure versus crank angle diagram, remember that for the data file that you're using, this period of time between negative 180 and positive 180, this is your compression and expansion strokes, okay? And that's what the gross work corresponds to, is compression and expansion. And so then the gross indicated IMEP, indicated mean effective pressure, is just going to be the gross work divided by the displaced volume of the cylinder. Okay? Pretty straightforward. It's very confusing at first because we're not used to having to take sort of these integral principles and actually apply them in reality with like a numerical technique of integration, but that's basically what we're doing. Okay? Okay, now what about the network? Well, the network is the work over the entire cycle. Okay, and so that's going to be from minus 360 to 360. So it's going to include the intake, compression, expansion, and exhaust strokes. Okay, so if we use our little handy dandy equation here, we can say that the network is equal to the sum from minus 360 to 360. Pi times the change in volume. Okay? So this is by far the most difficult thing of this particular problem on this assignment. And so once you have that mastered, you're pretty much good to go, right? So if we just look at some of the others, right? So that basically takes care of C and D. Okay, so the net indicated mean effective pressure is just going to be that net work that we just calculated divided by the displaced volume. The pumping mean effective pressure is defined in your notes, right? And so that's just the difference between your net and gross indicated mean effective pressure, right? And so you can see here that IMEP net is equal to IMEP gross minus PMEP. So PMEP is equal to IMEP gross minus IMEP net, okay? And then your brake mean effective pressure is also defined in your notes for you. And so that comes up a little bit earlier here, where BMEP is now the brake work divided by the displaced volume. And again, we're going to talk more about this in class, right, in terms of what brake work means. But you can calculate your brake work based on the brake power. P sub B is brake power, times the number of revolutions of the crankshaft per cycle divided by the speed of the engine times the displaced volume, okay? And so, another way to think about it, or another way to use this relationship, is if you just go up another slide, you can see here that your brake work is defined in terms of the torque, right? So you're given the torque in the spreadsheet file, right? So this is your torque right here, okay, in Newton meters. Be careful of newtons units in this assignment. And so your brake work per revolution is just 2 pi times that brake torque. But then you have to convert this brake work per revolution into the brake work per cycle, which means you take that brake work per revolution and multiply it by this N sub R, which is defined over here in the right-hand side of the slide for you, okay? So again, everything is provided for you to be able to do this in your Chapter 2 notes, right? The friction mean effective pressure. If you just scroll a little bit further down in your notes, you'll see a definition for friction mean effective pressure. Let's see here. Oh, I think I might have passed it. But basically, friction mean effective pressure is your IMEP net minus your BMEP. I can't find it. Okay, well, I'll make sure that I go over that in class real well. But just so that you know, friction mean effective pressure, I can go ahead and write that on my little notes here. Friction mean effective pressure, FMEP, is just equal to your IMEP net minus your brake mean effective pressure. It's basically quantifying for you how much work is lost due to friction, okay? And then finally, the last question is asking you to calculate the mechanical efficiency. And so that's just BMEP divided by IMEP net. I'll just go ahead and define that for you as well. So the mechanical efficiency, A to M, is equal to BMEP divided by IMEP net. And again, it's just telling you how mechanically efficient your engine design is, right? The higher the friction, the lower the BMEP, the lower the mechanical efficiency, okay? So most mechanical efficiencies are greater than 90%, but it's something that's good to quantify as well. And then finally, the last question I is asking you if the computed IMEPs are exact or approximations, okay? So a couple of hints there, right? If you think back to when you learned thermodynamics or you learned calculus in general, right? This is basically the precise definition of work, right? Whereas this is an estimation or an approximation. It's a numerical technique, so it's necessarily going to be an approximation to the actual calculation. So I pretty much gave you the answer there, but I'll let you think through it and just kind of think about how you best want to respond to that question. Okay, hopefully this video was helpful. And of course, if you have any questions, please feel free to reach out to me. And good luck with the assignment. Take care. Bye-bye.